I left this number of practice questions. Still, I have not received any feedback of late about what transpired and how you found them, whether complicated or something like that. Then we closed by talking about the derivatives of exponential functions. We said among the different types of functions that exist, the common ones are polynomial functions, but there are other equally very important functions that we talk about. One of them is exponential function, and the other one is logarithmic function. So we need to be aware. We need to know how best we deal with integration of such functions. So we have two rules that govern it. Before we get to the rules, natural logarithm is basically ln x, ln or log to base e. So here we rarely talk about the fundamental bases we are used to, such as log base 10, base 2, base 3, base 4, up to base 9. We don't talk about those. We only pay attention to the natural logarithm, since it is always used to benchmark any other equivalences in mathematics. So when you differentiate natural logarithm, you get 1 over x. So it is the same as differentiating ln x, you get 1 over x. Okay, you get 1 over x. That is a rule. The rule that relates to the exponential function ex is actually the derivative of ex is ex. Exponential function is neither affected by differentiation or integration, like we are going to see in a bit. Okay, so I remember I think we closed the discussion at that point and agreed to start from there. Okay, now, does paint allow writing? Let's see. Okay. So if you grab these two rules very well, then you must be able to do differentiation and integration. And here is an example. If we want to differentiate, actually most of the examples relating to differentiation of exponential function and logarithmic function calls for application of the chain rule. For one reason, we are having a function into a function. We are having a function into a function. For example, if we needed to differentiate log e x squared plus 3x plus 1, that is the same as ln natural logarithm of x squared plus 3x plus 1. The way we deal with that one, we must apply the chain rule. You are going to observe that even for other examples related to differentiating exponential functions also calls for the exponential function, for the chain rule. Okay, because we are seeing a function, x squared plus 3x plus 1 is a function. It is appearing within the function of natural logarithm. Therefore, chain rule is the most suitable rule. So if I let u be x squared plus 3x plus 1, I hope that is clear. Then that means that y is equivalent to log ue according to the substitution. If we substitute for u, then we get log u base e. Okay, I hope we are together up to that step. So if we proceed, we are going to differentiate. If we are to proceed, we are going to differentiate u with respect to x squared plus 3x plus 1 to come up with the du dx. Then, since we substituted u here, okay, since we substituted u there, we are going to apply, we are going to differentiate y, but with respect to u. We are going to differentiate y and understand how this y actually changes with respect to u to come up with the dy du. Also here get du dx. Okay, and once you do that, actually it is repeated here. Let u be this is u, okay, and from here we are able to get du dx. Okay, we are able to differentiate u, but with respect to x. Okay, we are able to to differentiate u, but with respect to x. Okay, once we get that well sorted, the next step is to differentiate. The next step is to differentiate y. Okay, is to differentiate y, but with respect to u. Since we have expressed y in terms of u, we can get du, we can get dy du. Okay, and based on the principle, it is the same as 1 over u. I hope that is making sense when you relate to the principles we have already seen. Any questions for me up to that level? Any questions for me up that level?
Someone was raising a hand. Sir.
Okay, please unmute and submit. Unmute. Okay, maybe no submission. So this is how the chain rule is stated, that if I need to find dy dx, I can pick that from dy dx. So if I need to get dy dx, I can get that from dy du, then times du dx. Okay, then we are going to substitute what we actually got from above. This is rho dash, just a second, jx ki dash okay. So we have dy du, we have du dx. We can substitute them. Just give me a second. Okay, this is sorted. Just 1 second. Okay. Okay. Let me stop sharing this. Stop sharing. Stop. Then let me share this working space where I can be able to write. This is doc 1. Okay. Okay. confirm you're seeing my screen. I want to put some examples. Now I can be able to write. So we are looking at an example. They want us to differentiate y equals to log base e. This is x squared. X squared plus 3x plus 1. Remember, we said that this one is actually the same as y being equivalent to the natural logarithm of x squared plus 3x plus 1. I have just mentioned that here we are seeing a function in a function, and we can let our u to be x squared plus 3x, then plus 1. From here, since u is expressed in terms of x, we are able to get dy dx as 2x plus 3. Okay, but in the same sense, our y will be equivalent to the natural logarithm of u, or our y will be equivalent to the log base e of u. Okay, and according to the principles, one of the principles of differentiation, we said that here our dy du is going to be 1 over u, and by chain rule, we know very well that our dy dx is going to be equivalent to dy du times du dx. Okay, and here we have our dy du, which is here, which is 1 over u, times our du dx. Our du dx is 2x plus what? Plus 3, and eventually, if we substitute for u, the answer will become 2x plus 3 all over divided by u, which u is x squared plus 3x, then plus 1. And this becomes the required dy, dx. So it is important that you appreciate this. Let's look at another example, but in terms of exponential function. Okay, they want you to find the derivative of e 3x squared with respect to x. When you look at this question, it is still a function in a function, and we have to first of all let y be equivalent to e power 3x squared, and also let OYU be equivalent to 3x squared. Like I mentioned in most of the examples about differentiation of exponential functions and differentiation of logarithmic functions will follow chain rule. Okay, if I let this one, you realize that when I substitute for u, even my y is going to be equivalent to e power u. Are we able to see that? Okay, if yes, then since our u is given in terms of x, we can easily get du dx to be 6x. Since our y is given in terms of u, we can still be able to get dy du, and this one will still be eu, because from the one of the rules we've seen this evening, u differentiation is not affected. Differentiation of exponential function does not affect the exponential function in any way. Okay, then you can apply the chain rule and say that by chain rule, if I need to find dy dx, this is dy du times du dx. We have dy du here, which is eu, times du dx here, which is 6x. And finally, on replacing u, we shall get our answer as 6x e 3x squared, and this one becomes the answer. So it should be noted that when dealing with exponential functions, and then
Excuse me, sir.
yes, please.
That answer cannot be simplified.
No, it cannot, because okay, it cannot because If you look at 6x, this is e and this 3x is power here.
Yes.
This one is an exponential function and this one is a linear function. There is no way you can simplify it any further.
Okay.
Yeah.
Thank you.
Okay. So that is it. That is it. You can find more examples in the notes for your further practice. For now, that's what I wanted to discuss as far as exponential functions and logarithmic functions are concerned in the line of differential calculus. I need to introduce a new topic at this point. Unless someone has a question, but if no question, okay, we need to touch. If no question, we need to start on okay. Now, this is integration, or you can call it integral calculus. Remember when I was starting that previous topic, I said that we are going to dwell so much on and calculus, which we have been discussing in the previous sessions, and then we have integration. Okay, now we want to understand the relationship, okay, involving the rate of change of two variables. Okay, that is what calculus is all about. For example, you want to know how the velocity of a body, okay, how velocity of a body changes with the time. To find this direct relationship between the two variables mentioned here, okay, to find this direct relationship between the two bodies, between the two variables mentioned there, can only be achieved using the process opposite to differentiation. And this process is called integration. Note, for any operation in mathematics, please note this very well. For any operation in mathematics, there should be always an inverse operation. For any operation in mathematics, there must be an inverse operation. Does that make sense? Inverse, the opposite. We must have the opposite. We can have examples, okay? In mathematics, summation and subtraction versus subtraction. So this is the inverse operation. When we do sum, that is adding. The opposite of addition is subtraction. Okay. Also, the opposite of division is multiplication. Okay. Even if we are looking at functions, even when we are looking at functions, even when you're looking at functions, for any function f, we can still get its inverse function f prime. That is sorry, not f prime. F prime is derivative, f power -1. Similarly, if we had matrices, for those who remember something about matrices, if we had a square matrix A, we can still get its inverse and come up with the inverse matrix. Okay? Now, for what we call integration, the opposite of integration is what we call differentiation. In fact, sometimes the reverse process of differentiation is called the anti-differentiation. Anti-differentiation is the same as integration. Okay? Now, I've been giving just a brief background for us to pick interest in understanding what integration is all about. To understand what integration is all about. Any question for me up to this point? Is the content flowing swiftly? Are you guys able to respond to me?
Yes, Mr.
Yeah, we
Chair.
are okay, sir. You continue.
Okay, great. That has been the background of this. Okay, also remember, for differentiation, if f of x is a function, then its differential calculus or different derivative is denoted as that. Okay. Now, for integration, please open your eyes widely here. For integration, if the integral, actually this is the definition, the integral of a function f of x with respect to x should be equivalent to capital F of x plus c. Okay, and what happens? This is c is called the constant of integration. Okay, and then this small fx here, this one, is also called the integrand. Sorry, that's not very clear. Integrand. It is called the integrand. Okay, also called the element of integration. This one can also be called the element of integration. Okay, then the capital F of x here is called the indefinite integral, or it can be called the antiderivative, or it can be called the primitive function. Okay, to compare notes, previously, let me insert a blank page here. Okay, it has come at the top. It's fine. It is very, very fine. Previously, we said for differential calculus that if I have a d by dx of the function f of x, then this one will give me the f prime x. And we had very many examples. For example, if this is x squared, then we shall get 2x. Principally, we multiply the power, okay, and reduce power by 1. Okay, and this is according to the power rule, which says that the d by dx of a function x power n then is going to be n xn minus 1. This is the generic rule. It is the most important rule when it comes to differentiation. I'm saying, or I have just said a few minutes back, that when we talk about integration, we want to understand the